Hello everyone, my name is Oded Shopen and I'm a Tanzu Solution Engineer at VMware. Today I'd like to walk you through the process of setting up Tanzu Application Service on Tanzu Kubernetes Grid. We are going to deploy Tanzu Kubernetes Grid onto a vSphere environment, followed by an installation of Tanzu Application Service using KApp. We will then deploy an open source UI management console for Cloud Foundry, and we will also connect our Kubernetes cluster to Tanzu Mission Control for easier management. We will also connect our cluster to Tanzu Observability by Wavefront for monitoring purposes, and we will create a database from the Tanzu Application Catalog. By the end of this video, we're going to have a simple web application with a front-end, back-end, and a database running in our cluster. Our first step is to deploy Tanzu Kubernetes Grid. And for that, we'll need to first deploy the OVF templates to vSphere. This is my vSphere environment. I'm going to create a simple folder called TKG, where it would be easier to manage all of my images and virtual machines. And now I'm going to click Deploy OVF Template. I will choose a local file and I will point it to one of the two images required to deploy Tanzu Kubernetes Grid. These images are available at the VMware download page for Tanzu Kubernetes Grid. And they are basically one of them is for the actual operating system that will run for our worker nodes or for the control plane. And the other one is a nature proxy that will allow us to load balance across our control planes in case we have more than one. I will accept the license agreement and I will choose a data store to deploy the OVF. And I'm also going to select a network that has DHCP enabled, which is required for TKG at the moment. I will now move to the second deployment of the Photon OS image. And same process, I'm going to select a data store. And I will also select a network with DHCP enabled. After a few minutes, my OVFs are deployed and I can begin the installation of Tanzu Kubernetes Grid. So I'm going to use the CLI TKG and I will run tkg init -ui in order to open a deployment console on my web browser. This will run a Docker image on my local machine. I will choose deploy on vSphere. I can also deploy on AWS if I'd like. And I'm going to provide the details of my vSphere environment, so the fully qualified domain name of my vSphere environment, the username, and the password. I will now click Connect, and I'll be able to see information about my environment through the UI console. So I'll select the data center that I'm going to use, and I'm also going to create an SSH public key that I can provide to the installation. So I'll run SSH keygen, and I'll provide a path for that. We'll call it TKG. And I will copy the contents of the public key to the UI console. Clicking Next. Now I can select if I'd like to deploy a development or a production environment. I will choose production in this case. I'll give a name to the management cluster. And I will select the HA proxy that we deployed previously as a load balancer across the control planes. Clicking Next again. I will choose the resource pool that I like to use, as well as a folder where my images or virtual machines basically are going to be deployed, and also a data store. Lastly, I'll need to select a network, and again, I'm going to use the same DHCP enabled network, and these defaults seem to be okay. I'll click Next. And I will select the operating system image to use, which is Photon 3 in this case. And my setup is complete. I can review the configuration and click Deploy Management Cluster. So what's going to happen now is that TKG is going to create a cluster that will allow me to create other clusters, basically. The cluster API, which is the standard that TKG is using, is basically allowing us to use Kubernetes to create Kubernetes. Right? The cluster API allows us to use Kubernetes native commands and configurations to provision other clusters. So the first thing we'll need to do is to create a management cluster that can deploy other clusters. After a few minutes, the installation is complete, and I can check the management console that has now been created, again using the TKG CLI. So if I'll now type TKG get management console, I will see the current management console that my environment is pointing at. And this is just another Kubernetes cluster, just like any other one. It has pods, it has namespaces, it has nodes. For example, if I'd like to see the information in the cluster API namespace, I will see that it has some pods up and running in here that will allow me to deploy clusters going forward. So now I'm going to create an actual TKG cluster that I'd like to use. I'm going to override some of the parameters here, some of the defaults. So I'd like to have 4 CPUs and 16 gigs of RAM for each worker node or control plane node. Actually 6 CPUs in this case. And first I'm going to run a dry run just to make sure that the YAML the TKG is creating looks okay, so I can confirm it, can review what is the creation here, and now I'll run it again without the dry run option, which will actually create a cluster called TAS, or Tanzu Application Service, in my vSphere environment. So if we'll let it run a bit faster for a few seconds, we will see that after a few minutes, we have a cluster up and running that we can actually use. And my cluster has been created, and it's also pointing to this cluster right now as the default cluster in my local environment. So the cluster itself has 3 control planes and 5 worker nodes that I can use to deploy whatever I'd like, and we will use this environment to deploy Tanzu Application Service. We can also use the TKG CLI to view the list of clusters it has created, and in this case it created a single one called TAS. Our next step is to set up cloud native storage in vSphere, and for that we'll need to set up a few tags and categories. So I'll go to tags and custom attributes, I'll move to categories, and I'll create a new category. Let's call it, for example, Kubernetes storage. And I can select what objects can be assigned this particular category. So I might select in this case just data store and data store cluster, maybe even folder, although it might not be mandatory. And I will click create. Next, I will go to storage, and I'm going to create a tag based on the category that we just defined. So I'm going to call this tag Kubernetes storage for LAN 01, and I'll assign it to the category that we just created. And I'll click assign. Now I'm going to go to storage policies, and I will create a new one. And this storage policy will be used by our Kubernetes cluster to determine where persistence volumes and persistent volume claims are going to be located. So I'll create a tag-based rule, I'll select the category, and I will select the tag that we just created, and I'll click next. The results show only the single data store that I have, so I'll click next again, and finish. So now I have a storage policy defined in vSphere, and I can go ahead and move to my Kubernetes cluster and apply a cloud native storage YAML file. So first of all, I'm going to check that I have no existing storage classes in my Kubernetes cluster. And now I'm going to define a YAML file for my storage class, and I'm going to point it to a storage policy name based on the storage policy that we just created. In our case, it's Kubernetes storage policy. So I'll type that in here, and the provisioner is vSphere in this case, and I will run apply. Now that the storage class has been created, we can see that it exists, and it is also the default one. And now we can move on to installing a load balancer in our cluster. This is not mandatory for Tanzu Application Service. However, it is preferred to access using a load balancer because it just simplifies a lot of things. So I'm going to use Metal LB in this case. I'm going to create a namespace, and I'm going to apply a YAML from their GitHub repository. And after everything has been created, I can continue to configure specific parameters for my own cluster. First, I'll need to create a secret. And now I'm going to edit a config map for this particular load balancer, and I'm going to set out a specific address space that it can use to provision load balancers. Again, I'm going to use the same network that I created before called extra, and I'm going to use some specific addresses for that. Once that applied, our installation should be complete, and we can run a quick test to verify that the load balancer behaves as expected. So I'm going to install a simple demo deployment application into my cluster to verify. We see that the namespace is up and running and everything runs as we expected. It assigns a daemon set for each one of the nodes in my cluster. So this is the test echo server that I'm running, and I'm scaling it up to 3 replicas. And I'm also exposing it as a load balancer. And now we can check the services and verify that I have an external IP for the echo deployment. And I can go ahead and test that it actually responds, and everything seems to be in order. So now I can go ahead and finally install Tanzu Application Service in my cluster. So I'll go to Tanzu Network, and I'll search for Tanzu Application Service for Kubernetes. There is an open beta available. I will download version 0.1.0, and it's a fairly small download. Once it's downloaded, I'll move it to a specific location that I'm using to install. And one of the things that you need to do before installation is to configure a few variables. First of all, I'm going to remove the YAML that says replace load balancer with cluster IP because I do want to use a load balancer in my case. So I'll just remove that. Next, I'm going to set up my system domain where all of my applications and system components are going to run under. So this is a specific URL that I have. You need to have KApp installed along with additional CLIs on your local machine. You can download them from k14s.io, simple installation. And in my case, I also want to use Bosch CLI to expedite the setup process. It is not required for the actual installation, just to expedite the interpolation of environment variables. So I ran the generate values script, and now I have a deployment values YAML available. And that's most of the environment variables that Tanzu Application Service will need to install. Various certificates and an admin password that was generated and the system domain that I provided. There are some additional properties that I will need to provide. In the installation guide, there's an additional method to do this activity. It can be done using an additional YAML file of application settings. Here I'm just exporting some environment variables instead. The environment variables are pointing to the VMware repository where most of the images are available. And I'm also pointing to a harbor registry that I have myself. This is where images are going to be deployed when I run CF push. So in this version of Cloud Foundry, when you run CF push, your actual deployment, the build packs, is going to create an actual Docker image and host it on a Docker registry. And only then will it actually deploy the application to Cloud Foundry. So you need to provide some form of Docker registry. It does not have to be Harbor. Here I'm just using Harbor because I have it already available for me. So with that out of the way, I can go ahead and proceed to the actual installation. I'm going to run the install Chaz shell script. And the installation shell script requires the deployment values YAML that we just generated as a parameter. And it's going to use an open source project called KApp, which greatly simplifies installations on Kubernetes. It has a full plan of how to install the various required components, including all of the steps along the way that have to complete before we can proceed to the next step. So as you can see here, it begins by installing Istio, and after a few minutes, the CF system is up and running. This is the main namespace with most of the components required for Cloud Foundry to work on Kubernetes. And once everything is up and running, we see that our installation is complete. If we'll take a look again at the CF system namespace, we're going to see a lot of deployments. And also under Istio, we can see that we have an ingress gateway with an external IP that we should map to the system domain that we defined earlier. I've done it already, and now I can just log into the API endpoint of my installation, and I will provide the skip SSL validation parameter because I don't have signed certificate in this environment. And we can see that the installation is successful. I'm now logged in to Cloud Foundry running on Kubernetes, and I can go ahead and actually deploy some application. So first I'm going to create an org, and I'm going to create a space, and I'm going to target this org and space. And I'm going to enable the Diego Docker feature flag, which is just a way to hint to Cloud Foundry that Docker images are supported in this environment. I'm going to deploy an application called To-Dos, which has a front end written in Node.js and the back end written in Spring. And as you can see, the manifest YAML for the back end is fairly straightforward. Just provide a path and a name. I'm going to build my project. And once it's built, I'm going to run CF push. Now this is an interesting point to pause for a minute. As you can see, I need to upload around 42 megabytes on the first run because I need to upload the entire jar file that was built from Spring. And this could take quite a while. Now if I run it a second time, as I'm doing right here, like in a classic Cloud Foundry environment, it's only going to upload the delta, so around 700 kilobytes this time. So below we are pushing, and above I'm viewing the logs. We can see that kpack is being used to build the Docker image with the correct layers and everything required. It's also pushing it to the Harbor registry that I defined earlier. And I can refresh Harbor and see that the image is now available for me. And it is also tagged as build number 1 and as the latest build currently available. Waiting additional several seconds, it is also going to connect Istio to my application, deploy it, and have it up and running. Now we can actually see the logs of the application starting. And if I'll go to the URL that I received from this environment and go to an actual endpoint that this application exposes, we will see that everything appears to be working as expected. Now here's something that you couldn't do before in a classical Cloud Foundry environment. With the support for cloud native build packs, basically the new version of build packs in this release, we don't have to compile the code beforehand using the whatever JDK is running on this machine I'm using. So I can remove the path variable from the manifest and just push the source code. I removed the jar file by running maven clean, and I'm running cf push again, and now it's just 120 kilobytes, just the source code basically. And again above we're seeing what happens behind the scenes using the build service of Tanzu and kpack. So like before, it is creating the various layers, but unlike before, it's also compiling my application now on the platform side. And it's also downloading required artifacts from Maven Central. And after a few minutes, it is again up and running. So if I refresh Harbor, I will see a new version of my application. This one is around 122 megabytes, while the previous version was a little smaller. So you can see that it actually created a different image. And again, the application is still working just like before, which is awesome. Now I'll move on to push my front-end code, which is written in Node along with Vue.js. The manifest is fairly straightforward. I'm going to build it locally this time. And I will cf push again. I'm using a random route initially here. As you can see, it created a random URL for me. And again, above we're seeing the creation of the build pack and it being pushed to Harbor. And then the application is going to start in my environment. So going back to Harbor, if we'll go to a different URL, we will see that this one is pointing to the front end and it has its own tag as we expect. And then proxy finished its job. And again, our application is up and running in the cluster. If we'll take a look at the applications that we have two of them, one front end, one back end. If we'll go to the URL for the front end, we will see that it comes up. However, it has an indication that it could not access the backend service. And that's because this application expects that both applications reside under the same fully qualified domain name. So I'm going to map a route that is going to be shared between both applications. Only the backend will respond to /API requests, and the front end will reply to everything else, basically. So route mapping is extremely simple in Cloud Foundry, and it works just as well while running in Kubernetes. So if we'll go again to our application with the correct fully qualified domain name, we see that now our application works as expected. The front end can call the back end, and everything seems to be in order. Next, I would like to deploy a UI console so I can easily manage my environment. Now, Cloud Foundry is an open API and it's an open platform under the Cloud Foundry Foundation. So even while running under Kubernetes, in theory, all the APIs should be exactly the same. So I can prove that by installing an open source project called Stratus in this case, which is available under the Cloud Foundry GitHub repository. I'm going to use Helm to install this service. And once I have it installed, I'm going to create an external IP for the UI dashboard. So taking the UI ext service and changing it to be of type load balancer should give me again an external IP that I'll be able to use to connect to this application. So like before, I created a domain name for this IP beforehand. And now, as you can see, I have Stratus up and running on my Kubernetes cluster. I'm going to create a local admin user, so it will be easy for me to manage. And once that's done, I can log in and I can begin attaching various Cloud Foundry endpoints to my management console here. So I'm going to connect to the deployment that we just created under Kubernetes. I'm going to point to the API endpoint and skip SSL validation. Once I register this endpoint, I will click connect and I will use the admin username and the password that was created when we generated the deployment YAML. And now we have Taz on TKG available on this environment, and we can view the different spaces and we can see the applications, we can query the data. Again, the API is exactly the same. It doesn't matter if you're running under classic Cloud Foundry or if you're running Cloud Foundry on Kubernetes like here. So I can change the routes, I can do whatever I would normally do if I were to run this application on any Cloud Foundry target. I can also see the environment variables that were created when I ran CF push that are all available here, and everything seems to be in order. So Cloud Foundry side seems to be working as expected, but I'm still running on Kubernetes. And it would be nice if I'll be able to manage my cluster from a single pane of glass once I grow in the number of clusters that I have. So I'm going to use Tanzu Mission Control for that. I'm going to basically attach the cluster that we created in the first step to this management console. And then I'll be able to do various activities such as creating a cluster group from multiple clusters or create a workspace from multiple namespaces, and also to be able to assign security policies across clusters. So in order to do that, I'm going to copy the line from the UI in here, and I'm going to basically run a kubectl create command on my cluster. This creates a vSphere system TMC namespace that is going to start communicating with Tanzu Mission Control. And after several seconds, Tanzu Mission Control will be connected to my cluster, and I'll be able to begin managing it from a single pane of glass. So as the components here are starting to come up, we can move to the various tabs here. For example, the nodes tab to see the number of nodes in my cluster. We can see the allocated CPU and the allocated memory. We see that I have 3 control planes and 5 worker nodes, and we can see the utilization for each one. So with the management out of the way, I would also like to add some observability to my cluster, and for that I'm going to use Wavefront. Wavefront can monitor pretty much anything we can imagine, including Kubernetes clusters, including Cloud Foundry. So I'm going to create a Wavefront namespace, and I'm going to, again, copy the Helm install command from the UI with my own personal token. And after several seconds, it's going to communicate back to Wavefront and let me know that my cluster is now available for monitoring and for observability. So if I go to the Kubernetes summary dashboard, I can see a lot of information about a specific cluster or across multiple clusters if I have that, like the number of pods and the number of containers running, CPU utilization, anything you can think of, you can probably monitor and observe it from here. There are multiple dashboards available out of the box, or I can create my own custom dashboards if I need to. For example, this is a dashboard for monitoring the various nodes and how much CPU is currently utilized in each one of my nodes. And again, I can have aggregated data across multiple clusters or just a cluster that I care about at any given time. I can also view a dashboard specifically for pods. And I can group the information, for example, based on a namespace. So as you can see here, there are only 2 pods running in the CF workloads namespace, which is where my applications are actually running at any given time. So if I'll take my application, the front end, for example, and scale it from 1 instance to maybe not 50, maybe 25, and we can see it begins to scale up, both in the UI and in the CF CLI. And even if we run a kubectl command, same data is being reported. I will do the same for the backend application. So the to-do service, I will scale it up from 1 instance to 10. And quickly, it's going to start. And we can see how many are currently running and how many are initializing. And we see that they're all running at the moment. And now we can see in Wavefront that there are much more pods in the CF workloads namespace, and we can drill down to each one of these pods and observe it specifically. And we see that each given pod has 3 containers inside, 1 for the application and 2 for Istio. And we can really drill down and get a lot of information on each one of the pods that are currently running in the cluster. So now that I scaled up my application, I'm going to try to use it again. And we're beginning to see there are some issues. So if I'll try to, for example, add a new entry like hello world again, we see it, and I'll add another entry, and now I'll try to refresh the page, and suddenly the information is gone. Where did it go? Well, the reason for this is that we now have more than 1 instance in the backend. So every time we're running an API against the backend, it goes to a different instance. And we are currently using, by default, the H2 in-memory database, which is different for each one of those Java Spring instances in the backend. So in order to resolve that, we'll need to create a real database, in this case MySQL, and bind this database to the to-do service application. So I'll go to Tanzu Application Catalog in this case, and I'm going to use a quick search to find MySQL. There are many different services in this marketplace. I'll need MySQL in my case, and I'll need to add a repository to my local environment, and then I'll be able to install MySQL. I already created this repo add command beforehand, and I called it TAC, so now I can just immediately run the install command using the TAC/MySQL command, and I'll need to provide a generate name in this case. And after a few seconds, it's going to have the MySQL database up and running on my cluster. And I'll be able to use the deployment to create a user-provided service that I can attach to my application. So I'm going to grab various passwords and IP addresses from the generated Helm chart, and I'll create a JSON file that I can feed to the Cloud Foundry API to create a user-provided service, basically looking at an existing installation of a database or a message broker or whatever it may be. So I have the caps.json file here. These are the various parameters that are needed by Spring in order to connect automatically to a MySQL environment. So I'm going to copy the URL and the database name and the username and the password in their correct location. And once I have everything set up, I'll be able to create the service. Now, this is, of course, something that usually will be done by a service broker automatically for me in a Cloud Foundry environment. But in this case, I opted to use a user-provided service, so I will need to handcraft this JSON myself. So now that I have a user-provided service available, I can bind this service to my application. In my case, the backend application, which can connect to a MySQL database. Once it's been bound, I will restart my application. And we can see in the UI console that indeed the application is up and running and it is bound to the MySQL user-provided service. And these are the parameters that it received. Only thing left to do is to refresh the application again, and let's see if it works. So, hello world from instance 1. And if I refresh, and lo and behold, the information is still there even though we're using a different instance. So everything seems to be in order now. And our application is now up and running. We can access it even from an incognito window, for example. Everything seems to be in order. So we created a cluster, a Kubernetes cluster. We installed Cloud Foundry. We monitored it with Wavefront. We managed it with Tanzu Mission Control. And we added a service from the Tanzu Application Catalog marketplace. I hope you enjoyed this demo and see you again soon.